Head modeling is an important part of the source estimation procedure. So everything you are doing afterwards depends on the accuracy of how well you can model head geometry and current flow in the head. Let's just remind ourselves what we are trying to achieve with our head modeling. By far the most commonly used head modeling approach is probably the boundary element model, or BEM. But what we are trying to do is we are trying to describe the relationship between our dipole sources in the brain, which we can assume as, let's say, little batteries that become active in a part of the gray matter whenever this part of the gray matter springs into action, and the measurements outside the head. And so we have to take into account the volume currents, which are caused by this primary current here. So this is the current of interest. This is what we are not really interested in. And so we want to understand the relationship between our dipole sources and our measurements. In order to do that, we have to be able to describe what happens in terms of volume currents if there is a primary source with unit, or dipole with unit strength in a part of the cortex. So what kind of volume currents would that produce, and how is that then reflected in our measurements? And then later we can use that information to get back from our measurements to the primary source, the source of interest. The boundary element method models the head in terms of enclosed compartments. So the important thing here is to know what the conductivities are, and in particular conductivity boundaries between different parts of the head, because that determines the strength of the current flow. So it's one thing is the physics, the electrostatics of the problem, but in order to do this in practice, we need to know the geometry of the head, and in particular how the conductivities differ across different types of tissue and between the source and the sensors. And in the boundary element approach, we assume that there are a few compartments which are enclosed within each other that have different types of homogeneous conductivity. And usually this is the brain, the skull, and the scalp. In this case, it sort of looks a bit like a potato. It's supposed to look like a realistically shaped head. It could in principle be a spherical model as well, but at least that's the way we approximate the reality. And ultimately, what we need for our head modeling are these types of information. We need to know where our sensors are relative to the brain. So we have to co-register our imaging modalities somehow, because MRI and MEG data are usually not measured in the same coordinate system. Same for EEG. We somehow have to make sure we know the right locations of the EEG electrodes on the scalp. We need a source space that's often the cortical surface or the three-dimensional volume of the brain. And then we need our compartments for the head model, for the boundary element model. And that would be the scalp and the outer and inner surfaces of the skull, for example. More detailed head models are available or can be computed, but this also very much depends on how good your MRI images are and how much time you want to spend on segmenting these surfaces from your MRI images. But this is very much a standard approach if you have individual MRI images available. I don't want to bore you too much with the physics, but these physics are quite well understood. The problem is usually in how to implement all of this in practice with numerical methods. I would say most software packages will offer you reasonable methods to do that. So you describe the current flow, and in particular the jumps of the currents across boundaries that change with respect to conductivity. So that's why it's called the boundary element model. And here just a few things that I probably mentioned already in some other sessions. So we have to make sure that we take into account all volume currents, and they depend on the conductivity distribution within the whole head volume. And EEG measurements are actually the result of these volume currents. So these volume currents that reach the scalp, after they struggle through the brain and the skull and the scalp. So they create voltage differences on the scalp. and they are strongly affected by head geometry. So for EEG, we have to make sure that we get an accurate, our head model right, as accurately as possible. MEG measurements are the sum of magnetic fields from primary and volume currents. So MEG is also affected by volume currents, but magnetic fields are usually the currents are much closer to the primary source than further away from it, and especially in the skull and in the scalp, the currents are much smaller than in the brain. So it means MEG is less affected by these volume currents than EEG, but it still is affected. And therefore, MEG signals are less affected by head geometry. So in principle, it could be a bit more sloppy with head modeling with MEG. And therefore, if you only have MEG data, then in some software packages, you would only use a BEM model that actually includes the inner skull. So you wouldn't even bother to use the other compartments. But for EEG, and especially also if you use MEG in combination with EEG, then you should at least use these three compartments. And there are studies that have looked at differences between head models with respect to localization, accuracy, or with respect to the overall relative error in the electric and magnetic field distributions. So there's one study here which looked at quite a few anatomical models. So what type of information you take into account, and then what kind of head model you make out of it. So I don't want to get into too much detail here. I mean, these are different types of MRI images and how they were processed. And these are different head models like 3-shell boundary element model. This is an approximation based on local spheres, 1-shell boundary element model. Oh, sorry, this is the local sphere. This is, I think, a multipole approach. I'm sorry if I don't remember the details right now. And this is the single shell model, probably the most simplistic approximation, just with a single sphere. In this case, red color means that you have a high relative error with respect to the ground truth in these simulations. And not surprisingly, the more simplistic your models are, also the more simplistic your anatomical models are, the higher these relative errors, especially in areas that probably cannot be modeled very well in terms of the spherical approximation of the head. So the head is roughly is close to a sphere, but I guess mostly in the front and in the back. It violates this kind of spherical shape. So that's where you get the largest errors. But within this range up here, where you have relatively realistic head models, especially with a 3-shell BEM model, the relative error is relatively low. So I would say with a BEM model, you usually have a reasonable approximation of the truth. Also in this study, I mean, it was a relatively simple way of checking how robust the boundary element model is with respect to conductivity errors. So we simply underestimated or overestimated the conductivity of the skull. And then we looked at the relative error with respect to the ground truth. And in this case, this was all done in simulations. And relative error could be up to 20%. But if we actually look at the correlations of the true topographies for dipole sources and those that we get with under or overestimated conductivity, then I mean, look at the scale here. So we are always very close to 1. That means the conductivity of the skull mostly affects the overall amplitude of our signals, but not the shape of their topographies. And if you use distributed source estimation methods, minimum norm beamforming, or the like, then it's usually the shape of the topographies that matters. The overall amplitude is basically like just a scaling parameter, if you like. So we actually think that we can be sure that boundary element models are relatively robust against conductivity errors. Having said that, of course, the real world is more complex. So these are all just different approximations. You could model the head as a sphere or maybe several spheres within each other. But as we've seen, then you can make quite significant errors in some brain areas. A boundary element model is a relatively efficient way of modeling at least the most important features of the head geometry. But you can, of course, say, well, conductivity changes probably even voxel by voxel in the brain, and definitely for different types of brain tissue. So you can actually model or segment the brain into lots of different voxels and have different conductivities and even non-isotropic conductivities in different compartments. So this would be a finite element model. So these models are more complex, harder to implement, but they exist. But I couldn't resist just briefly saying, well, already in the 80s, it was really cool when these kinds of segmentations appeared. So I was quite mesmerized when I saw these heads, by Kraftwerk floating around the screen. So back then it was really cool and was novel, and probably took them quite a while to get this going. These days we can do things like that within minutes. Always getting a bit nostalgic when I see figures like that. So maybe a couple of words on this finite element model. So as I said, 3-layer BEM models are very much the standard, I would say, state of the art in EEG, MEG source estimation if you don't have any special requirements. And for MEG only, you can even use single shell BEMs. But reality is always more complicated. So as we can see here, you have various different tissue types in the head. This is only a small overview here. And they all have different conductivities. It could even be more complicated. For white matter in particular, you might even have different conductivities in different directions of the tissue. So nerve fibers might have different conductivities along the fiber rather than perpendicular to it across the membranes. So you can make things arbitrarily complicated. However, even if you can in principle model these things with finite element models, I think the bottleneck is still that you actually need to know the values of these conductivities. And this is quite hard, I think, to determine. There are, of course, literature values. So all the different types of tissue have different conductivities from the literature. In this case, they don't really provide any standard deviations here, but I think from my reading of the literature, there can be quite different values depending on how these values were obtained, from living organisms or dead organisms or directly, indirectly. So I'm by no means an expert on these things. But yeah, this is definitely, if you want to use these methods, I think this is certainly something to look into. So how reliable are these values? And where would you want these methods? One obvious application would be damage to the head or to the brain, especially when the skull is damaged. You may want to make sure, especially for EEG measurements, that this is taken into account in your model. I found nothing really that I could present here in my talk. So if anyone knows any good studies that have modeled that and are good for a presentation like that, then please let me know. But another example I found was that of infant skulls and fontanelles and sutures. I guess most of us know that baby heads, the skull is still developing, so there are big gaps in the skull at the beginning after birth, and then within the first period of our lives, they close. And if you want to record EEG in particular, but also MEG from these infants, then the standard head model might not work, especially in areas directly underneath these fontanelles and sutures. So this is something that, this is a case where if you want to do source estimation with these data, you need to take this into account. Okay, this is just a really brief overview of the principles of head modeling. So usually it's, I would recommend to look at the tutorials in your particular software package and see how this works in practice, and inspect your MRI images, your head models in the end, make sure that the surfaces you segment out of your data are what you expect. And also in another session, we talked about sensitivity maps. For example, you can check how sensitive your sensor configuration is to different parts of the cortex. So once you've done all your head modeling and you think you're ready to do source estimation, maybe spend 1 minute looking at these sensitivity maps to make sure it all looks plausible and that the head model is indeed, does indeed do a good job.